Okay, so welcome to AMS 1D tutorial sessions. This is the AMS 1D program, not the WX AMS that you might find on Angel. Okay. So in order to have AMS 1D, what you need first is Windows XP because AMS 1D only works up to Windows XP. So if you happen to have any of these operating systems, such as Windows 7 or other operating system, including Windows 8, you have to follow these instructions to get Windows XPs. So if you have Windows 7 Professional or up, you have to go to Microsoft.com to download and install Windows XP Mode. It's a virtual machine that you can use Windows XP with it. If you have any other operating system, you can use this link on this presentation to get VMware Player, which is a free software to give you the virtual machine that you can install Windows XP on it. Now, with the exception of Windows 8, you can follow these instructions to get Windows XP. Now, if you're a Penn State student or faculty and staff, you can follow this link and use your PSU ID to sign in or register if you haven't already registered yet, and download everything, including Windows XP, for free onto your virtual machine. Others can download Windows XP Home Premium by following this link. Okay. Now, for AMS 1D installation, you can all go on to the website www.amsmodeling.org to request the files and then install it into the Windows XP that you got on your virtual machine. And let's just say you did just that. So this is AM1D that I got on the virtual machine environment, just like you did. So from here, you can open a new case by hitting this button. So in this new case, as you can see, the first thing is device diagram. And as the name suggested, AMS 1D only simulate one-dimensional device structure, which means it only simulates structure that has layer by layers, planar, just like this. And you can simulate how many layers you want, and it will be capped by the front contact and the back contact. And detail information can be changed by these three buttons down here. So before we go into the layer info, let's notice that the DOS or density of state model is checked, which means when you run this case, it will use this particular model to simulate your device. If you want to use a lifetime model, you need to check it. Let's use the DOS model for now. So the first thing you need to go to is layer info. You hit layered info, it will give you this new window where you have no layers yet, but you can add one by hitting this button. Let's just say that I'm going to simulate an N-type silicon single crystal silicon layer. So when I hit OK, multiple things become available to me. And if you look down here, all these numbers, all these parameters are defaultly for silicon. If you use any other material, you need to change these numbers. So, as I say, I'm going to simulate an N-type silicon, which is signified by having some sort of donor concentration. Now, the donor concentration can be changed by changing this parameter, ND. let's say that I change this to 1e17 or 10 to the 17, 1/centimeter cube concentration. I hit OK. My change is confirmed. Second thing is the layer thickness. Now defaultly, the layer thickness is kept at 100 nanometers. I can change this number to anything I like. Let's say I change it to 500 nanometers. And as you notice, as I confirm my change to the layer thickness, this number changed. In order to simulate the device, AMS will divide your layer into multiple grid points. So the more grid points you have, basically the more accurately your simulation will be. But sometimes more grid points doesn't mean your simulation will be a lot more accurate. So it's a good thing to keep in mind that AMS limited this number to 400. So that if you have multiple layers, it's a good idea to keep the total number of grid points in your device less than 400. Anything more than 400 will not be necessary to simulate in terms of accuracy. Now you can manually change the number of grid points in each layer by changing the center grid spacing. Let's say I change this number to 10. As you can see, this number changes. So let's look at these buttons up here. Now, in this tutorial, I'm not going to go into details of what band tail and gap state is. More information can be referred to by reading the manual available to you in the installation files. Let's just talk about this button, absorption properties. If I click it, it will be this window. So if you use AM 1.5G as your illumination spectrum, you can just simply hit this button. If you use any other spectrum, you have to enter manually. For now, let's just use AM 1.5G. So if I hit that button, the number of wavelength, or lambda, will be available to me. Each wavelength will be a corresponding flux. And these numbers are particularly for AM 1.5G and not any other spectrum. So in this column here is the absorption coefficient of the layers I want to change. For now, is the N-type silicon that I just made. These are the default values, and they should be changed. And you can change each number by double-click on it and change to anything you want. Change the number, I hit enter, and I can hit OK. And my change is recorded. You can do this to the last value of wavelength. Right below this column is the optical band gap of this particular material. You can change this number to anything you want. It's a good idea to keep it the same as the band gap that you have on the outside. Now defaultly, it is the same band gap. Now defaultly, this is the silicon band gap. Okay. And you can compare this layer with any other layers if you have them. confirm this by hitting OK. So practically, this is how you keep making your layers. Let's confirm all my changes for now. Now the next thing you want to do is to change the parameters of the front contact and the back contact. Let's go to the front contact first. There are 4 parameters here. The first one is phi b0. Next one is SN0, SP0, and RF. Let's first talk about the phi b0. Now phi b0 and phi bl, as you will find in back contact, use a very similar formula. Phi b0 is the difference between the work function of the front contact metal and the electron affinity of the semiconductor in contact. Now, phi bl is the same. Difference is it's a work function of the back contact metal with an electron affinity of the semiconductor in the contact. So I can change this number to anything I want. Now to understand a little bit more about phi b0, let's talk a little bit about the metal semiconductor contact. Now there are 3 basic metal semiconductor contacts. The first one is ideal ohmic contact, or sometimes called flat band. Now you can achieve this when the metal work functions or the Fermi level of the metal line up with the Fermi level of the semiconductor, where they're not in contact. When that happens, when you put them in contact, you would have essentially flat band and conduction band edge, and flat band and valence band edge. The second one is selective ohmic contact. As you can see, that's essentially another material here with a slightly larger band gap than a semiconductor. Now what it does is it's essentially block the movement of holes in the valence band go into the metal, where allowing electrons go into the metal. Hence the name is selective. Now the third kind is called the Schottky contact. Now this happens when the Fermi level of the metal and the Fermi level of the semiconductor don't line up when they're not in contact. When you put them in contact, there's charges that exchange between the 2 materials. And this exchange will cause the conduction band and the valence band edge bend at the contact. Now, Schottky contact is also another kind of selective contact, where it hinders the movement of holes going into the metal and allows the movement of electrons into the metal. Now you can achieve both of these contacts, the Schottky contact and the ideal ohmic contact, by manipulating the Fermi level of the metal and the semiconductor. The select ultimate contact can be achieved by just adding another material with a slightly larger band gap. So getting back to amps, we're still in the front contact. Sn0 stand for recombination speed of electrons, or N, at the front contact. And Sp0 is the recombination speed of holes at the front contact. We need these two numbers to create a boundary conditions for our simulation. The last one is RF, or reflection coefficient at the front contact. Now essentially, when RF is 0, all light will go through. When RF is 1, all light will be reflected. Now you can see here, light goes in from the front. So it's a good idea to keep this number anything other than 1. For now, let's just keep it at 0. Back contact. Similar concept. Let's keep the PBL 0 for now. And let's change the RB, or the reflection at the back contact, to become 0, to become 1. Excuse me. That means all light, when it approaches here, will be reflected back. So let's look at these 3 buttons in the middle here. The first one is voltage biasing. What voltage biasing does is it will simulate your device from 0 volt to 1 volt at each of these steps. You can get the dark IV characteristic curve and the light IV characteristic curve because of these voltages. In the illumination conditions, defaultly, light is off. What it means is you only get the light, the dark IV characteristic curve, and you won't get the light IV's characteristic curve. If you turn the light on, you have multiple options. This option only gives you the light IV characteristic curve. This one gives you the light IV along with the spectral response. And the rest. Now you hit the spectrum parameters, it will give you the same windows when you click the absorption property of the layers that you want. Let's keep the light off for now. So we're ready to save our case and simulate this device. In order to save this case, then go to File and hit Save As. And you can change this to anything you want. Now, it's a good idea to keep this name as simple as possible and no space or any special character. You save it like this, the case will not run. So we're ready to simulate. In order to simulate the case, you can hit this button called Submit Case to Queue. You can say yes. So the case finished simulating, and when it does, it will give you this notice. If you hit this button, it will delete all the simulation results and let you manipulate anything in the layers. For now, most things will be unavailable to you. So in order to see the simulation result, we can go into this button. You can choose whichever case you have open. For now, let's see the band diagram. So I picked conduction band at thermal equilibrium. I'll add that to the plot list. The program knows that you're trying to plot the band diagram, so narrow down the options. You can pick the Fermi level at thermal equilibrium next, the valence band edge, the vacuum level. So we're ready to show the band diagram. So this is the band diagram of our device. The front contact is here. You can see the band bending of the semiconductor due to the contact with the front contact. And you can also see very slightly the band bending that happens in the back contact. This region is sometimes called the space chart neutral region, where the conduction band, the Fermi level, and the valence band remain unchanged over the distance. As you can see, this is an N-type material, just like I said, where the Fermi level is very close to the conduction band edge. Up here is a vacuum level. So what we have here is typical of two Schottky contacts, in the front and in the back. So if I want to change this band diagram to perfect flat band in the front and the back contact, I can close this. I can close this. I can recess the case. And I can change this PPO number to something that will give me the flat band, which in this case is somewhere around 0.14 EP. And I will do the same for the back contact. Now, if you don't wish to change the name of the case, you can just hit this button. It will save the case for you. And you can start simulating the case. Again, we're going to go to plot. Select the case that you want to plot. Select the conduction band. As you can see, band diagram changes now. And it's very close to flat band. It's not exact. But this is our band diagram. And now these contacts are very close to ideal ohmic contact. Now you can save these plot as data if you select this button, Save Data to File. And you can change to any name you want. And make sure that the extension is some sort of text file. For example, txt. Now you can use that to plot the data anywhere you want. So the next question is, what about the light IV characteristic? Before we do that, we open a new file. Now this file is an example file that is located within the folder of AMS1D. The program files, locate Penn State folder, AMS1D, locate the samples folder, and you have two sample cases. First one is PIN amorphous silicon, and the second one is PN silicon. Let's choose a PN silicon for now. Now this case has already been made and simulated. As you can see, that is saved with simulation result. Let's see what's different about this case. In this case, we have an addition of the P layer of silicon. The only difference is the P layer would have the acceptor concentrations. That's not 0. The spectral parameters is already input in for P silicon and N-type silicon. Are essentially the same. One contact. CPO is 0.7 eV. SN0 is 1/10 to the 3 centimeters per second. SP0 is 1/10 to the 7 centimeters per second. RF is 0. That contact, VBL is 0.5 eV. SNL is 10 to the 7 centimeters per second. SPL is 10 to the 3 centimeters per second. And RB is 1. illumination condition, light is on. That means we will have the light IV characteristic curve. Let's see what we have here. First, let's see the band diagram at thermal equilibrium. We have other options here to show you the band diagram when light is on at different voltage biasing. Now in the band diagram, you have additions of the electron quasi-Fermi level and host quasi-Fermi level, which is only available when you turn the light on. So this is a band diagram of our device. The P layer is 5 micron thick, and the N layer is 5 micron thick. We have the very famous PN junctions right in the middle. Now before we plot the dark and light IV characteristic curve, let's clear these plot. We go back to this column and try to locate the dark and light IV characteristic curve. Notice these numbers. The most important one is JSC, which stands for short circuit current. EFF is efficiency. FF is fill factor. VOC is open circuit voltage. Okay, the dark one, the black one is dark IV. And the red one is light IV. We only care about this region here. So let's zoom in. First, let's zoom in somewhere very close to the open circuit voltage, which was 0.636 volts. So let's use 0.5 volts. For J, or current density, the open circuit voltage, the short circuit current was 28 milliamps per centimeter squared. So let's do 40 for example. We essentially zoom in. Very similarly, you can extract the data by selecting this curve and then save data to file. This is essentially all you need to know to run AMS1D.